Welcome to week 10 of Classical Mechanics 2. I'm Sabeta Matsumoto, and this week we're beginning our third and final unit, rigid body rotations. This is a busy week during the semester for all of us, so this week we're just going to be reviewing some concepts from rotational motion, namely angular momentum and torque. At the end of these videos, we'll combine these ideas together to start thinking about angular collisions. Last week, we used the Lagrangian and Hamiltonian formulations of classical mechanics to explore central forces and special properties of the inverse square law. That system relied heavily on the concept of conservation of angular momentum. For the rest of the semester, we're going to combine that with the ideas of continuous mass distributions that we studied earlier in the semester in order to explore the full dynamics, 3D rotations, and translations of rigid bodies. Extended bodies can undergo two types of motion: linear motion and rotational motion. In linear motion, we can treat the entire body as if it were a point mass located at the center of mass of the body. The center of mass is defined as RCM is equal to the sum on I of MI RI divided by the total mass of the object, if this is an object that's created from a bunch of point masses. Or if it's a continuous body, this is the integral of R dm divided by the total mass. It turns out that this is only true because we're in Euclidean space. If our space had curvature, then there's no well-defined center of mass. This is partly because curved spaces aren't vector spaces, so we can't just sum up the position vectors the same way we do here. But it's also because in curved space, there is no single point that we can reduce an object to so that all of the physics acts on that point. And this is actually something that my group is studying as a way of generating translational motion in extended bodies in curved spaces. For linear motion, the basic quantities we consider are mass, velocity, acceleration, momentum, which is mv, force, which is ma, or equivalently the rate of change of momentum, and kinetic energy, which is 1/2 mv squared. Rigid bodies can also undergo rotational motion. So imagine we have an axle here, and it's rotating at some rate, omega. All of the quantities for linear motion have rotational analogs. These are moment of inertia, which is the sum on I of mi ri squared, or equivalently the integral of r squared dm. It's the analog of mass. Instead of velocity, we have angular velocity given by the vector omega, whose magnitude is given by the rate of rotation, and it's oriented along the axis of rotation with sign given by the right-hand rule. We can take the derivative of this and we get angular acceleration, which is alpha. Instead of momentum, we have angular momentum, which is either r crossed into the momentum or equivalently I times omega, and these are both vectors. Instead of force, we have torque, which can be written in a variety of different ways. Like force, it is equal to the moment of inertia times the angular acceleration, or equivalently, the rate of change of angular momentum gives us torque, or we could use r crossed f as our torque. And for rotational motion, we also have a kinetic energy, and this kinetic energy is given by 1/2 I omega squared. First, imagine that the axle we're going to rotate about is fixed. So it's going to be right here, and we're rotating about this axle at rate omega. Let's look at what happens to an infinitesimal mass element, dm, that's located at distance ri from the center of rotation. The angular momentum of this element is given by Ri crossed into its momentum, which is dm times Vi. If the whole body is rotating at angular frequency omega, then dm has a tangential velocity given by Ri times omega. So our angular momentum is now Ri crossed into dm, the magnitude of Ri times omega, and this is in the direction of the velocity. When we take this cross product, we end up with Ri squared times dm times omega, and this is pointing in the z hat direction, in the same direction as omega. To get the total angular momentum for this system, we need to integrate across all possible mass elements. So that gives us an angular momentum that is omega times the integral of r squared dm. Since we're in the xy plane, r squared is just x squared plus y squared. This integral here gives us the moment of inertia about this object rotating about an axle that is in the z direction. That gives us omega times the moment of inertia in the z hat direction. This object has kinetic energy that is given by 1/2 times the sum on I of mi vi squared, which when we turn our v's into omegas, we end up with 1/2 omega squared times the sum on I of mi ri squared. Equivalently, we can write this as 1/2 the integral of r squared dm, and this is going to look pretty familiar. That's going to be exactly the same integral that we have up here. So when we rewrite this, we end up with 1/2 iz times omega squared. Let's imagine now that our object is both translating and rotating at the same time. For the translational motion, we'll assume that it's moving at some constant velocity, vcm. The distance from the origin of our coordinate system to the center of mass is given by rcm. And again, we're going to look at what happens to an infinitesimal mass element, dm, which is located at distance r prime from the center of mass, or distance r from our origin. From the origin of our coordinate system, this mass is located at rcm plus r prime. And the velocity of this point would be given by the velocity of the center of mass plus the velocity relative to the center of mass. We can calculate this by pretending that the center of mass were at the origin. This object is rotating about the center of mass with some angular velocity, omega prime, which tells us that the magnitude of v prime is going to just be omega prime times r prime. We can use this to calculate the total angular momentum of this object. This is going to be given by the integral of r cross the momentum of all of these infinitesimal mass elements, which is v dm. And if we plug in our definitions, we end up with this here. Now let's take the cross product of these terms. The first one we'll look at is these two terms here. So this is going to be RCM cross VCM times the total mass of our object. That's just the angular momentum of an object that is traveling at velocity VCM with mass m. We have another term, which is r prime cross v prime integrated over dm. This gives us the angular momentum of some rigid body traveling at a constant velocity. And then this term over here is going to be the angular momentum of the same body rotating now about its center of mass at some angular velocity omega prime. This is a bit reminiscent of the parallel axis theorem. So imagine we knew the moment of inertia of our body about its center of mass, and we want to figure out what the moment of inertia for a body rotating about some other axis that is a distance r from the center of mass, but the two axes are parallel. What the parallel axis theorem says is the moment of inertia about this new axis is just the moment of inertia of the body about its center of mass plus mr squared. The kinetic energy here is going to be, again, a sum of the linear kinetic energy, so 1/2 mvcm squared, and this rotational energy about its center of mass. And so this might be reminiscent from quantum mechanics. This is similar to the way we split up angular momentum and energy into an orbit piece and into a spin piece. For the rest of this, we're just going to calculate the moments of inertia for several objects that we're likely to see again. For all of these objects, we've got the moment of inertia is equal to the integral of r squared dm. For each of them, we're going to identify what r squared is, what dm is, and then do this integral. The first object we have is a hoop that is rotating about some axis that is perpendicular to the plane of the hoop, and the hoop has radius r and mass big M. So this tells us that our radius is just going to be r, and dm for us is just going to be rho r d theta. So we can integrate this now. We have I is equal to the integral from 0 to 2 pi of rho r cubed d theta, which gives us 2 pi r times rho times r squared. And this, you'll notice, is the total mass of our system. So our total moment of inertia is just mr squared. Let's look at the same hoop, only now instead of spinning through an axis perpendicular to its plane, we're going to rotate it about an axis that passes through opposite points on the hoop. Here we have a radius, which is the distance from the axis, is r times sine theta, and our infinitesimal mass element dm is rho times r times d theta. So here we've got a moment of inertia, which is the integral from 0 to 2 pi of r sine theta quantity squared times rho r d theta. When we do this integral, we end up with 2 pi r times rho, which is again the mass, times r squared over 2, or 1/2 mr squared. All of these moments of inertia will be written down in the form some numerical constant times the total mass of the body times a length squared. If instead of a hoop, we imagine we've got a disk of radius r and total mass m, we're going to take as our mass element these infinitesimal little hoops. Our radius is equal to r, and our infinitesimal mass element is equal to 2 pi rho times r dr. This is going to give us 2 pi times the integral from 0 to r of rho r cubed dr, which is 2 pi rho times r to the 4th over 4. We can rewrite this to pull out a factor of mass. So this is 1/2 times pi r squared rho, which is the mass, times r squared. So this is also going to give us a moment of inertia of 1/2 mr squared. What about a rectangle of side lengths A and B, which is rotating about its center perpendicular to the direction of its plane? The distance from the axis is the square root of x squared plus y squared, and our infinitesimal mass element is just rho dx dy. Our moment of inertia is now the integral from minus a over 2 to a over 2 dy, the integral from minus b over 2 to b over 2 dx, times rho x squared plus y squared. When we do these integrals, we end up with 2 rho times b a over 2 cubed divided by 3 plus a times b over 2 cubed divided by 3. And we can rewrite this to pull out the total mass. We have 1/12 times the total mass times a squared plus b squared. Or equivalently, our total moment of inertia is 1/2 m a squared plus b squared. These are all planar objects. We can do exactly the same thing for non-planar objects. Our first example is going to be a spherical shell. This is a sphere of radius r, and our infinitesimal mass element is going to be this little circular ring here. The distance of this ring to the axle is just going to be r sine phi, and our infinitesimal mass element is 2 pi rho r squared sine phi d phi. And now we can combine this all together into a giant integral, which is 2 pi times the integral from 0 to pi of r sine theta quantity squared times pi r squared sine phi d phi. We can gather terms. This is 2 pi rho r to the 4th times the integral from 0 to pi of sine cubed phi d phi. And this integral here just gives us 4/3. So if we want to re-express this in terms of m, the easiest thing to do is just multiply this by 1. So we've got mass divided by 4 pi r squared rho, and we end up with our total moment of inertia is 2/3 mr squared. Instead of a spherical shell, next we're going to consider a solid sphere. So here our infinitesimal mass element is a disk of radius little r, where little r is given by r squared is equal to the radius of the sphere squared minus the height of the disk squared. Our mass element is given by pi rho r squared dz. We're going to solve this in a slightly different way than we've solved the other ones. I already worked out the moment of inertia of a disk for you. So what we're going to do is we're going to add up all of the infinitesimal moments of inertia of these disks and integrate them. So the moment of inertia for a disk is just 1/2 mr squared. The moment of inertia for this infinitesimal disk di is equal to 1/2 r squared dm, which is equal to pi over 2 times rho times r squared minus z squared dz. And now we can integrate this. So this is pi over 2 rho times the integral from minus r to r of r squared minus z squared dz. And this gives us 18/15 pi r to the 5th times rho. And now we can multiply it by 1 the same way we did before, where the total mass is just 4/3 pi r cubed rho. And this gives us a moment of inertia, which is equal to 2/5 mr squared. So you'll notice that objects that have more mass concentrated towards the center or towards the axle have a lower moment of inertia than those that have mass further away from the axle. In the next video, we'll review how adding external forces and torques change the behaviors of these systems. See you next time. It's a noisy night, so hopefully this recording will go okay. Nope, I'm a little bit out of order here. Omega. Okay. Noisy motorcycle. I don't know how these guys keep doing this acceleration-y thing twice.